Okay, so chapter 11 talks about conic sections. The first one we're going to talk about is the parabola. Parabola is one of four different conic sections, and I kind of always enjoy thinking about what Greek mathematician was a couple thousand years ago, sitting around with as much idle time as Jeff on a Saturday, and and pondering, gee, what if we took two cones, placed them tip to tip, and then sliced them with a plane? What would the intersection look like? Wow, turns out that the intersection is exactly the kinds of shape we're going to study. So if you slice parallel to the sides of one of those cones, then you're going to get a shape called a parabola. If you slice perpendicular to the axis of symmetry, you'll get a circle. If you incline that plane slightly from perpendicular, you'll get an ellipse. And if you slice parallel to the axis of symmetry, but away from the center, you get two parabolas that face away from each other called hyperbola. So, wow, spot on. But again, I wonder who was thinking about that first. Now, what's different about this class as opposed to your Math 1150 class is that we're actually going to find a little bit more information. The definition of a parabola is the set of points that are the same distance away from the center point, that is your focus, and a line down here. So if I were to measure this line up to this point and this line down to here, that distance would be the same. And that's true no matter where you're at along this curve. So a couple things that we're going to look for. One, we're going to try and figure out where that focus point is. And the other thing we're going to have to figure out is the directrix. So a little bit more work than what we did with your previous class. But let's see some of the applications. Where would you see the shape of parabola? Well, once you lay down the deck, the cables of a suspension bridge are going to be in a parabolic shape. Newton used a parabolic mirror for his telescope. And if you want more about telescopes, Jeff can tell you a lot about telescopes, I'm sure. It had better optical properties than the Galilean telescopes that existed until now. Radio telescopes have been in existence since the 1950s, and they're amazing. If you were to light a match on the moon, they could spot the flare. They are so sensitive that the total amount of energy that they've collected in their 50, 60 years of existence is less than the snowflake hitting the ground. One snowflake. They're just amazingly sensitive. So if we have a mind to spot something in the universe, we usually can. Angry birds, yeehaw. All right, parabolic shaped arc there. And this one's kind of cool. Kind of a homegrown example, the Hubble Space Telescope being worked on by Andrew Feustel. Now, what's special about Andrew Feustel? He's an OCC graduate. So when we say you can get anywhere from here, we mean it. So, cool deal. This is a nice confluence of technologies. If you put a parabolic shaped reflector on the top of a building, then you can use fiber optic cables to bring sunlight into the interior of a building. Searchlights, and where would we be without the grunts and groans provided to us by a parabolic microphone on Monday Night Football? So, lots of applications for the parabola. Let's learn a little bit more about it. So, I mentioned that we're going to have to find the focus here. Now, that focus is a distance we're going to call P away from the vertex. So here's the vertex of your parabola. That distance is P. And the distance from the vertex to the directrix is also P. So this distance overall is twice P. Now, this is the definition of parabola. One thing to keep in mind about a parabola, the focus is always going to be on the inside of a parabola. I remember seeing kind of a pseudo magazine cover. They were playing on the National Enquirer kind of magazines. They say a parabola with a focus outside of it. You know, it's really dirty pictures or something. Parabola always faces away from the directrix. So this is the orientation that you should get used to. The parabola is going to envelop the focus and face away from the directrix. It'll never cross its directrix. There's a couple different forms of the equation of a parabola. We've worked with both of these. If a is greater than 0, what direction does your parabola open in this case? Good. A is greater than 0, opens up. A is less than 0, opens down. That's for a parabola in y squared. What's the vertex of this one? Can anyone tell me? What's the vertex? What would the coordinates of that vertex be? Yep, h and k. H and k is your vertex. You should be able to read it off if it's in that form. If it's not in that form, if it's in this form, then you can at least find the coordinates of the vertex by using this formula. Negative b over 2a. And once you have the x coordinate, you plug in x to get the value of y. Now either way you express it, a is going to be the coefficient of your squared term. And if you were to go through the derivation of the equation of a parabola, you'd be able to see where this comes from. But p is going to be 1 over 4 times a, and that's going to tell you the distance from the vertex to the focus, or the distance from the vertex to the directrix. But p is 1 over 4a, and I kind of suggest that you have both of these formulas in mind. A equals 1 over 4 times p. We're going to use them both. We don't have to limit ourselves to just parabolas that open up and down. Question? Yeah, so, yeah, one side or the other. So if you have a parabola in y squared, x equals a times y minus k squared plus h. Again, this still has a vertex at k for y and h for x. So it still has the same coordinates for the vertex. It looks a little bit different. Let's understand a couple things about this. If a is greater than 0, which way do you think this thing is going to open? Good. It opens to the right. So positive in y squared opens to the right. Opens right. Then obviously if a is less than 0, it opens left. Cool. Now there's something else that we'll spend a little time on, and it's called the focal diameter. So if you take, and let's draw a couple lines here in our parabola. There's one through the focus. That would be your vertex. But if you draw a line through the vertex, line through the focus, then this distance is called the focal diameter. And that distance should be exactly 4 times p. So we'll see that as well. Now, throwing a lot of information at you. A couple things that I'd like you to see would be that the orientation of the parabola and which way it opens. So we'll practice those first. We'll start with problem number 6. So this is in your book, and really what they're doing is asking you to play a little mix and match. So let me get the right page here. It's on page 788. And let's see if we can't figure out what to expect from parabolas like this. So this is y squared equals negative 1/4 x. It'd be nice to solve for one of these variables. Which variable do you think it looks easier to solve for, x or for y? I think I would multiply both sides by negative 4 and rewrite that as negative 4y squared equals x. So you've got x by itself. What can we expect from a parabola like this? Is it going to open left to right or up and down? Yeah. Because it's a parabola in y squared, it's going to open left or right. Because of the negative coefficient here, it's going to open which way? To the left. Are there many candidates for that correct parabola amongst the 6 choices that they give you? Which one did it have to be? It has to be 5, right? That's the only one that opens to the left. So 6 goes with 5. Let's try another one. So problem number 8 is 2x squared equals y. Well, 2x squared, that's just going to be a regular parabola, right? Which way does it open? Y equals 2x squared. Has to open up, right? So again, not too many choices. And the last one, let me come back down to the last one. Again, you might want to rearrange this a little bit. I'd start out with 12y equals negative x squared. Y equals negative 1/12 x squared. Well, has to open down. Okay. So there's 2 choices here. Either 2 or 4. Which one of those do you think is the correct choice? How could you figure it out? 4? Okay. I mean, they look kind of the same, you know. But why 4? You're right, but why 4?
1/12, so it'll open wider.
Yeah, the 1/12 is going to open wider. If you look at this scale, the scale here is a 2 and a 1. This thing is actually opening wider. You can plot some points. For instance, if you plug in, I don't know, pick your favorite point. X equals 2. 2 squared is 4. 4/12 is really 1/3, so negative 1/3. So 2 and negative 1/3, yeah, that looks reasonable. All right, so the last one, 10 goes with 4. Let's try a few more. Let's take a look at problem number 32 next. So it says, find an equation for the parabola that has vertex at the origin and satisfies the given conditions. So problem 32, want to find something with a vertex at 0, 0. And a focus of 0, negative 1/4. So let's kind of draw that a little bit. Focus is at 0, negative 1/4 down here. Which way does this parabola have to open? Up, down, left, or right? has to open down. Because remember, your parabola is going to open around your focus. So you have a couple choices. You have, y equals ax squared or x equals ay squared. But it can't be this one because the parabola is going to open up or down as opposed to left and right. And further, we know that a has to be less than 0. So the question, what is a? Well, they tell us this much. They tell us what p is. P is 1/4. Actually, it's -1/4. So p equals -1/4. And we can use that to find a. What's your expression for a? Feel free to look over on the front side of your handout. Good, 1 over 4p. So a equals 1 over 4p, which is 1 over 4 times -1/4. What does a equal? A equals -1. So the parabola that you're dealing with is really y equals -x squared. How are we looking on
So for
32? Yes, go ahead.
when you find out A or P and you plug it into the A equals 1/4 P or P equals 1/4 A,
Mhm.
you can just substitute A for Y and P for X squared.
No. You wouldn't be substituting p into this formula. What we're doing is we're going to calculate a. So sometimes we'll use a to get p, sometimes we'll use p to get a. But p does not appear in the formula directly. You have to get p kind of in a roundabout way. So through this formula. Other questions on problem 32? Let's try problem number 34. This one happens to be on our graph. So we've got a focus at 5 and 0. The vertex is at the origin. Taylor, here's two formulas here. X equals ay squared, y equals ax squared. Both of them will result in a parabola, but which one of these can I eliminate? Which one won't be the case for problem 34? Let's think about what our parabola has to look like. We've got a vertex here at 0, 0, and the focus at 5 and 0. Which way does our parabola have to open? All right, to the right. So something roughly like that. So Taylor, which one of these can I eliminate? Some help, Alan? Which one can I eliminate? Okay. Well, something times x squared is going to open up and down. So we can eliminate that one. This one has to open to the right. So that's what I was getting at on this one. Now the only other thing then is to determine what A is. And this part right here is telling us something. What's it telling us? It's giving you the value of P, right? So what does P equal in this case? P equals 5. A equals 1 over 4 times P, which is 1 over 4 times 5, or 1/20th. And with that, just plug that into your equation. Overall, we get 1/20th times y squared. Yeah, go ahead, please. Say again? Well, there's two formulas, and they're both equivalent. I mean, you get one from the other. Let's see where So right here, P equals 1 over 4A, and A equals 1 over 4P. So they're kind of symmetric. You can derive one from the other. If I was to multiply this on both sides by 4A, I get 4AP equals 1. And then if I divide both sides by 4 and P, I get that. So once I have this, I can get that one just by rearranging it. So they're just two sides of the same coin. Yes. But that's it for problem 34. Let's try another one. The one to the right here. Kind of a similar thing going on. We've got a directrix at y equals 6, so that's this line right here. And again, a vertex here. Let me start this one the way I started the last one. X equals ay squared, or y equals ax squared. Which one of these can I eliminate? Both. Well, a could be negative.
X and y equals ax squared is the one you want.
Well, which way does it have to open?
I said you is the one you want.
All right, so is this one going to open up or down? Ooh. Up, down, up, down. Take a look at the front side of your handout. Does the parabola cross the directrix? No. So it can't open up, can it? It can't even open sideways. What direction does it have to open? Has to open down. So if it opens down,
Your focus is at 0, -6.
good. This distance is P equals 6. Actually, -6, if you want to be very, very formal. So P equals -6, but it's opening down, just like Lucas said. So A equals 1 over 4P equals 1 over 4 times 6.
-6.
Thank you, -6. Because you're going down. Down or to the left would be -6. You know, you bring up a good point. Personally, I don't like keeping around the mental gymnastics of, is it +6? Is it -6? Here's what I do, or here's what I would do if no one's looking over my shoulder, if I wasn't doing this in class formally. And maybe we'll do it as well here. We know that this distance is 6. So, you know, before Lucas caught me omitting the negative sign, I would have come up with 1/24th. And then I'd write down my equation, 1/24th x squared. Then I look at this, wait a minute. That's wrong because it opens down. So, okay, I need the negative. So I think the easiest thing to do is just to not worry about, gee, is it positive or negative based on the orientation of the vertex and the focus. Rather, just find this distance, calculate A, and then put in the negative if you need to. So, appreciate the question. All right, how are we looking on problem 6 there? Okay? Or, well, this problem, I forget which one it is. Let's try problem number 14. Y squared equals 3x. Okay, so this one's graphed. It's a little bit different. That's okay. We need to play around with this a little bit to figure out where P is, or what P is. Now to figure out P, what do I need to know? I need to know A. Can I look at this and figure out what A is? Not yet. In order to figure out what A is, you have to have your non-squared term by itself. So either the x or the y has to be by itself. So I'll divide both sides by 3 and get 1/3 y squared equals x. Now I can determine what A is. A equals 1/3. So if A equals 1/3, let's determine what P is. P equals 1 over 4 times A, which is 1 over 4 times 1/3. Ooh, who can do all the mental gymnastics on this one? What is P going to equal? Close. It's going to be 1 over 4/3. And 1 over 4/3, well, you're just taking the reciprocal of 4/3. So it's going to be 3/4. So P equals 3/4. What's 3/4 as a decimal? 0.75. And ooh, isn't that special? We already have that point right there on our graph for you. How thoughtful. Now they ask you to graph this, and they want you to include a couple things. They want you to find the focus and the directrix. Do I have enough room on this graph to draw the directrix? No, that's okay. So the directrix would be over here. The equation of the directrix is something we can figure out, though. Remember, this distance right here is your P. P equals 0.75. That's to the right to find your focus, which is at 0.75 and 0. But if I went the other direction, 0.75, I'd have a vertical line which represented our directrix. Bonus points. What would be the equation of that vertical line?
Y equals, x equals 0.75.
Future to the left, so negative 0.75. Or negative 3/4. So that would be your directrix. Because it's just going to be a vertical line to the left of the vertex. The last thing to do is to figure out the focal diameter. That's a line that runs through the focus and touches both sides of the parabola. And I want to know what these points are. What are their coordinates? How am I going to figure out the coordinates of those points? Well, you should be able to tell me one of the coordinates, right? What's one of the coordinates here? 0.75. Let me write that out as 3/4. It should be positive 3/4 because you're talking about the x coordinate. The y coordinate is, you're right, is going to be negative. So how am I going to find the y coordinate then?
You just plug in your x
Yeah, plug in x in here. So let me go back to the original equation and plug in the value for x. So I'll get, let's do this in red here. Y squared equals 3 times 3/4. So y squared equals 9/4. So y is going to be plus or minus square root of 9/4, which is plus or minus 3/2. So there's your plus and minus, Lucas. So we have 3/2 here, negative 3/2 down here. Let's figure out the length of this. What's the overall length if I went from top to bottom here? What's the distance between positive 3/2 and negative 3/2? 3/2 minus negative 3/2 would be 6/2 or 3. Now that matches a conclusion that I gave you earlier, and that is the focal diameter, this distance here, is 4 times this. 4 times 0.75 is 3. But it's a nice confirmation of our calculations. How are we looking on 14? So I'm ready to give you one. Maybe we'll do it together. We'll see. But we did a lot on 14, so if there's something you have, a little question, here's a good place to get it answered. All good. Let's try problem number 24. I'm going to cheat. I'm going to give myself some more room by going to a different sheet. Eight x squared plus 12y equals 0. So good exercise to try and figure out what p is. Before I figure out p, what will I need? I need a. Can I say a is 8? Probably not. Before you figure out what a is, you have to have the squared term on one side and the other variable isolated on the other side. So I could start out with 8x squared equals negative 12y. Negative 8 over 12x squared equals y. And we should simplify negative 8/12 as negative 2/3. So we get y equals negative 2/3 x squared. That should help us out. What's a then? Good. A is negative 2/3. That's this right here. So once you have y solved for, then you can get a. A is negative 2/3. Use that to figure out what p is. Then try and give me the coordinates of p and the equation of the directrix. Cooper, what'd you get for p? Okay, so good. So 1 over 4 times negative 2/3 is your negative 8 over 3. You could all... no, not quite. What it'll give you is 1 over negative 8 over 3. But then we got to take the reciprocal, right? So when we take the reciprocal, we'll get negative 3 over 8. The decimal value for that is 0.375. So that's going to be your point here down on the focus. 0 and negative 3/8. Paige, what's the equation of this horizontal line here, please? Yeah. I'm going to write it as a fraction, but you're free to write it as a decimal. Y equals 3/8, 0.375, either way. But this distance is P, and this distance is also P. Now, I'm not sure if I really want to, if I'm going to ask you about focal diameter or not. But maybe one thing I could do that certainly wouldn't be too bad is just ask you what's the focal diameter. Not necessarily ask you to find these points, although we can. Maybe we should. But what's the distance here? Not 4A. There you go, 4P. So this distance equals 4 times P. Now they put it in absolute values. That's fine, in case P is negative. 4 times negative 3/8 is going to be 3/2. Or the absolute value of that is going to be 3/2. If you're to actually solve this equation to try and find these points, you could do that by plugging in values for, let's see, which one do I want to do? Plug in a value for y. The value for y would be negative 3/8. Then you'd solve up here for x. When y equals negative 3/8, you would get x is 3/4 and negative 3/8, or negative 3/4. And again, negative 3/8. It was kind of funny and sad at the same time. The Hubble Telescope, the one that I showed you the picture of earlier, when they first sent it up, it had a flaw in its mirror. It wasn't a big flaw. It was like about 2/millionths of a millimeter, or 2/millionths of a meter. Really, really small. But it was enough that it threw everything off. And so for a while, we had a $1 billion nearsighted telescope. Fortunately, and this is kind of the stranger than fiction part, they actually sent up corrective lenses for our telescope, and it works fine now. But that little part of it, the optical part, was nearsighted for a while.
The instruments they sent up after that had the corrective stuff in the actual camera, so like their original correction isn't on there anymore.
Really?
They had like 4 servicing missions.
Yeah. I think they're done servicing it
Yeah,
though.
it's done.
Yeah.
But James Webb right around the corner.
Cool. How are we doing on this one? Now, from time to time, you might want to look at these things on your graphing calculator. For this part of the test, I'm certainly not going to be letting you come up and use Desmos. That would be for the linear programming part. But if you wanted to, you could graph some of these things on your graphing calculator. The problem is you'd have to actually solve the equation for y. So I think this is actually, I reworked this handout, and some of the changes didn't get saved for whatever reason. This equation is negative 8y squared equals x. So if you wanted to graph that, well, in order to graph our problems on our graphing calculator, you have to solve for y. So the first thing you do is you divide both sides by -8. So I get negative x over 8. And then realize that when you take the square root on both sides, that there's really a positive and negative square root. The positive square root is going to give you the top branch. The negative square root is going to give you the bottom branch. You can plug in your formula into your calculator, and you have to plug in both of these. You can plug in the positive one and the negative one. I actually showed you a little bit of a shortcut for plugging in the negative one. So you can play with that. Instead of just typing in the opposite of the first one, you could actually just type in negative the square root of -8, negative x over 8, if you don't like all the commands for that. But the summary of the commands is right here, so you might want to play around with that at your leisure on Saturday when you got lots of time. Okay. Yeah. All right. Let's see. Let's do one last problem like this. We'll call this one problem 55-ish. And again, I want to go over to Desmos. And I'm really bummed that the email that I thought I sent out didn't make it to you guys. Let me sign in here real quick. All right, so graphs. All right. Yeah. Parabolas, open graph. Okay. Boom, boom, boom. So one of the cool things about Desmos is that you can import pictures, which I kind of like. And in particular, let's see if we can't fit a parabola to the Mackinac Bridge. Well, the cables here. Now, from the looks of things, it looks like I've got a center or vertex at -1 and -1. So, okay, that'll be my first guess. Y equals x plus 1 squared minus 1. And at least I got the vertex right. But it still seems like I need to adjust something, doesn't it? So what could I adjust to make this a better fit? What do I got to do so that this curve looks more like this one? Yeah, I got to adjust A. So let's take that out. And I put in a 0.1. And I got pretty close. So then I tried another one. I tried 0.04. And that looks pretty good. Now the reason it's not spot on is because this isn't precisely right, dead center, head on with the bridge, but it's pretty close. So there's our vertex, -1, 1. Now let's assume though that we actually managed to center this so that the vertex is at the origin. And let me talk about the Mackinac Bridge for just a second. So let me go back over to here. I'm trying to remember. I think if you go up to Mackinac, there's actually a little shop someplace along the main drag that has kind of like a museum, and I think about 5 workers died when they built that building, or they built that bridge, I should say. So a couple things about the bridge. The distance between the two towers is 3,800 feet. So 3,800 feet. And the height of the towers is 352 feet. Suppose I wanted to create a parabola that matched this. What general form would the parabola have? which one of these models should I use? Y equals ax squared or x equals ay squared? Yeah, has to open up, so that eliminates this. Now, if that total distance is 3,800 feet, then that means this distance here is 1,900 feet. What's that tell me about the coordinates of this point? Don't make Jeff do all the work. Somebody tell me the coordinates of this point, please. Olivia? Well, to the right and up, 1900 and 352. So if our parabola goes through this point, then I can plug that in. That would mean that 352 equals a times 1900 squared. And then just a matter of solving for a. 352 divided by 1900 squared equals a. And I'm sure we can put that in lowest terms. It's not going to be really pretty, but you can put it in lowest terms. But that's your a. And that's all we had to do to solve for a. Is just realize that, that 1 point is on this. Let's see if we can't simplify 352 over 1900 squared. I'm wondering if, change it to a fraction is actually going to help on this one. I think that'd probably be too small. Yeah, answer to fraction is too small. So, let's see, 1900. I'm not going to play with it now. Let's just leave it like this. Y equals 352 over 1900 squared, x squared. And that's your equation. Did you figure out? I think it turns into like 80 something, 84, or what this would be in lowest terms. It's all right. I'm not really worried about it. For homework, try 5 through 19, 23, 25, 29 through 37, and 41 through 47. That's section 11.1.